This is section 5.1, estimating with finite sums. You'll be able to estimate distance, areas, volumes, and accumulations using finite sums. Well, let's say we had an object and traveling 7.5 miles per hour the entire time. So let's say from 7 o'clock to 9 o'clock, the question would be, well, how far did this object go? Well, if you take miles per hour, so that would be on the y-axis, miles per hour. Let's write it like this, miles per hour, and multiply times hours, those would cancel out and you're left with miles. So the area under the curve is actually how far this object went. Now, we traveled for 2 hours going 7.5 miles per hour. So 2 times 7.5 is 15 miles. But what if instead of the object traveling the same speed the entire time, what if the object sped up and slowed down? Well, we would still find the area, but we need kind of a systematic way to find that area. And that's where this LRAM and RRAM that we're going to do later comes in. But let's talk about example 1 here. Consider a snowstorm that starts at 3 a.m. over the first 2 hours. The rate of snowfall increases from 0 to 1.2 inches per hour. For the next 3 hours, it continues to fall at 1.2 inches per hour. At 8 a.m., it begins to taper off, decreasing at a steady rate until the snowfall ends at 10:30. Find the total amount of snow that falls during the storm. Well, if we have inches per hour and we multiply by hours, those cancel out and we're left with inches. So we want to find the area under the curve. We have a triangle to start out with, 1/2 times 2 times 1.2. Then we have a rectangle, 1, 2, 3, 3 by 1.2. And then we end with another triangle there on the end, which is 2.5 hours times 1.2. So 2.5 times 1.2. And we got the calculator here. We'll just go 1.2, because those cancel out, plus 3.6 plus 0.5 times 2.5 times 1.2. So it ends up being 6.3 inches of snow has fallen. Find the total distance traveled when velocity varies again. A particle starts at x equals 0 and moves along the x-axis with velocity t squared for time t greater than or equal to 0. Where's the particle at t equals 3? So we're going to use 3 rectangles, and we're going to use left-Riemann approximation method. So here's 1, 2, 3 rectangles. And we're going to raise this up until the left side hits the curve. Well, the left side hits the curve right away on that one. Here's the left side hitting the curve. Here's the left side of this one hitting the curve. Now we can see this has lots of error in estimating the area under the curve, but we're only using 3 rectangles. So now all of these are 1 by plus 1 by plus 1 by. These are all have a base of 1. Now the height is following the curve. So 0 squared, we're using t squared, 0 squared is 0. Then we're using the height right here is following the curve. So we're going to plug 1 in. 1 squared is 1. And then here's the left side. That's going to be the height, which is following the curve. So if we plug 2 in, we get 4. So 4 plus 1 is, the area we estimate is 5. Now that's a big time underestimate because we have all this space that isn't even accounted for. So an underestimate. Let's go midpoint Riemann approximation method. So here's the base of the rectangle, and we're going to raise this up till the middle of the rectangle hits the curve. So we're going to raise this up till the middle hits. There's the middle. Raise this up until the middle hits. So there is the third rectangle. Now we got a little bit of overestimate, a little bit of underestimate. So this should be a fairly good estimate of the area under the curve. Kind of got a big underestimate there, a little overestimate there. But anyway, we have a 1 by 0.5 squared. That's this rectangle right here. And it's following the curve again. The midpoints are following the curve. Plus a 1 by 1.5 squared plus a 1 by 2.5 squared, because we're trying to find that function value up there. That's going to be the height of that rectangle. So 0.5 squared plus 1.5 squared plus 2.5 squared. So 8.75 is the estimate on that one. And here we're going to do a right Riemann sum. So we want the right edge to hit the curve. So right edge to hit the curve, right edge to hit the curve. right Riemann approximation method. So 1 by 1 squared is 1. So 1 by 1 plus 1 by 2 squared is 4. And 1 by 3 squared is 9. So 9 plus 4 is 13, plus 1, so 14? I'm getting 14. Now we have a nice, Desmos has a nice program that will calculate all these estimates for us. So if you go to my schedule on at least this year, it's on the 19th, but it's with section 5.1, RAM Desmos graph. If you click on that, we put the function in here, and our function is x squared, and we're starting at 0. We're going to 3, and we have 3 triangles, or rectangles that we're using. This says choice of method, set c equals 0 for left-hand sum, c equals 1 for right-hand sum, and c equals 0.5 for midpoint. And we're getting an estimate of 5 on left. And if we look back at our estimate, it was 5. Now if we click over to make this 0.5, now the estimate is 8.75, and that's what we got, 8.75. And then over to the right, the estimate is 14, and we have an estimate of 14. How about 6 partitions? We're going to do the exact same problem, except we're going to use 6 rectangles, and we're going to use left endpoints. So left, 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 and one more left right there. Now this is going to be, all these are 1/2s. 1/2 by 0.0 squared, 0.5 squared, 0.1 squared, 1.5 squared, 2 squared, and 2.5 squared. Now we're not going to have this one because that one doesn't, the height doesn't go up to, the curve on 3, it goes up to 2.5 for that last rectangle. All right, well we got 1/2 times 0.5 squared plus, not 0.1 squared, but 1 squared rather, not point. 1 squared plus 1.5 squared plus 2 squared, which is 4, plus 2.5 squared. All right, so our estimate is 6.875, 6.875. And the more rectangles we use, the better the approximation is going to get, because we're going to reduce the number of errors. Now I'm going to go back to Desmos. So let's go back to Desmos, and if you notice, let's have a whole bunch of rectangles. What if we got up to 56 rectangles? Then the right sum would be 9.24, midpoint's 8.99, and we have 8.7. Well, compare that to when we had 3 rectangles. It was 5, 8.75, and 14. That's a horrible estimate. But the more rectangles you use, the better the approximation is going to be for all 3 of them. Imagine all the way up to 500 rectangles if we use that. We have 9.027, we got 8.999, so they're all roughly 9. They're converging to be the exact same value. So the more rectangles we have, all 3 are going to converge to the true value of the area under the curve. Graph the region defined by the graph of f of x is 4x minus x squared, and let x-axis and the x-axis from 0 to 4. Partition 0, 4 into 4 subintervals and show the 4 rectangles that LRAM uses to approximate the area R. All right, so left, left, all the way up here. That's a left, and then this is a left right here. So there's the 4 rectangles. So we have a 1 by 0, you plug 0 into this, you get 0, plus a 1 by, plug 1 into here, you get 4 minus 1 is 3, plus a 1 by 8 minus 4 is 4, and then the last rectangle is a 1 by, plug 3 in, which is 12 minus 9, which is 3. So 3, 7, 10, the approximation is 10. And then I kind of already covered using the RAM program and showing what happens when you go to 500 rectangles. So let's skip that for this one. I did that already. Estimate the volume of the sphere. Estimate the volume of the sphere of radius 4. Well, we're going to estimate the sphere, but notice that we have this circle, and we're going to use cylinders to estimate this volume. and the radius of each of the cylinders is following that circle. Now, the volume of a cylinder is pi r squared h, and all the radii are following this curve. So that means that square root of 16 minus x squared, there's the radius. Now the height for each of those cylinders, we're going from -4 to 4, which is 8 units, and we have 8 cylinders. So the height is going to be 1. And that's really just, we're going to say that the height is the change in the x. When we do this process, we're not going to actually put that value in there. We're going to get that using the intervals and how many cylinders we have. So I'm going to go back to Desmos to do this, and I'm going to put the equation in. If you type pi and then times 16 minus x squared, because we're squaring that square root. And we're not going to put the height here, because we can get that by going from -4 to 4 with 8 subintervals. Now that's going to give us the correct height of 1 on each of those. And I have something not quite right here, because that is, yeah. Oh, we want mid. That's right for left endpoints, but if you look at the m's right here, that says mid. We want that approximation. Boom. 270.176. So 270.176. Well, we know what the volume of a sphere is. It's 4/3 pi r cubed, which is 4/3 pi times 4 cubed. Let's grab the calculator. 4/3, I'm going to turn it on, 4/3 times pi times 64. So that's there. Look how close the approximation is, 270.176 to 268.082. How close that is, only using 8 cylinders. Pretty remarkable that we can get that good of an answer, and we've only used 8. That's not like 800. We could use 8,000 with computers and get a really great estimate for this. A particle starts at x equals 0, moves along the x-axis with velocity v of t equals 25 minus t squared for time t greater than or equal to 0. Where's the particle at t equals 5? Approximate the area under the curve, distance traveled using 5 rectangles of equal width and heights, termed by LRAM, MRAM, and RRAM. So I'm just going to do one of them. So here's 25, 1, 2, 3, 4, 5, and there's the 0. So now let's do LRAM. 1, 2, 3, 4, 5, like that. 1, 2, 3, 4, 5. So now each of them are 1-bys, because we're going from 0 to 5 using 5 rectangles. And if I plug 1 into this, we get a 1/24, plus a 1 by, plug 2 into there. I plug 0. 1 by, if I plug 0 in, we get 25. Then 1 in, then 2 in would be 25 minus 4. Got to plug 3 in, 25 minus 9 is 16. Got to plug 4 in, which is 9. I'm not going to plug 5 in, because that's over on the right. See, that's not a height under, that following the curve. So 25 plus 24 plus 21 plus 16 plus 9. We get 95. 95. Use RAM to estimate the area of the curve of the function natural log from 2 to 6. So we're going to use, it says the RAM program. Now if it says the RAM program, then we're just going to plug in, we're just going to use that 500 subintervals. We use the highest value this will go to. So natural log of x, we're going from 2 to 6. 2 to 6 with 500 subintervals, and so we're going to say it's 5.364. 5.364, using mid. I mean, why not? 5.364. Distance traveled, the table below shows the velocity of a model train engine moving along a track for 10 seconds. Estimate the distance traveled by the engine using 10 subintervals of length 1 with a left endpoint values and B right endpoint values. Well, if we were to plot this, 0 would be 0, 1 would be 12, so be up here at 12. 2 would be way up here at 22, and so on. 3 would be back down here at 10, and we'd have this curve like that. So if we use left endpoints, we're going to start here. That'd be the first, then we're going to come up here, then we're going to come up here, then we're going to come up here. And the point is, on a left, we are not going to include this value right there, because that's a pure right endpoint. Now, each of these have a base of 1. So we can factor out the 1 and multiply by 1. So really all we're doing is adding 0, 12, 22, 10, 5, 13, 11, 6, 2, 6. And even though it wouldn't make a difference, we're not adding in this value right here, which happens to be 0, which wouldn't make a difference. But if it wasn't 0, it would be a big deal. So 87 inches. Now for B, for doing the right, we're going to have right endpoints, so we don't include the first value, but we do include the last one. So it's 12 plus 22 plus 10 plus keep on going, and we do add that 0. Now in this case, since the first and the last happen to be 0, it ends up being the same answer. Not a great example, but for LRAM, you don't do the last one. For RRAM, you don't do the first one. Particle starts at x equals 0 and moves along the x-axis with velocity that for time t equals 0. Where's the particle at t equals 3? So 0, particle starts at 0, velocity, where's the particle at t equals 3? So this has a y-intercept of 6, 1, 2, 3, 4, 5, 6, and a slope of -2. So down 2 over 1, down 2 over 1, down 2 over 1. And there's the curve from 0 to 3. And if this is the velocity, the displacement, or how far the particle travels, is the area under the curve. So 1/2 times 3 times 6, so 9. We're at 9. Particle starts at x equals 0, moves along the x-axis with velocity of that. Where's the particle at t equals 4? Approximate the area under the curve using 4 rectangles of equal width and height determined by the midpoints of the intervals. So t squared plus 1. T squared plus 1 looks something like this. And we're going to, where's the particle at t equals 4? With 4 rectangles. 1, 2, 3, 4. So what are we doing, R or L? Particles, using, oh, mid. We're using mid. So mid, mid, up here like that. Mid, up like that. And mid, up like that, right there. So all of these have a base of 1, a 1 by 1, 2, 3, 4. 0.5 squared plus 1, 1.5 squared plus 1, 2.5 squared plus 1, and 3.5 squared plus 1. So there's the 4 rectangles. 0.5 squared plus 1, plus 1.5 squared plus 1, plus, am I hitting the plus? 2.5 squared plus 1, plus 3.5 squared plus 1. All right, so 25.